Yeah. Where's my pen? Here's my pen. All right, I think we're gonna catch up in just here in a second. Uh yeah. What's up, guys? Kristen Ninja here, and welcome back. Yes, I know it's been a minute. Welcome back to Study Sessions. I'm your host, Kristen Ninja, and today we're going over control systems. Um, going over control systems. So let me how do I freaking there we go. Okay, so control systems. We have an exam coming up in this class, coming in like a couple days, No big deal or anything like that. Just try not to fail. um, so I haven't done the homework for this class that was used to like help us like learn this stuff, but I'll probably do that tomorrow, honestly. But the first thing I want to do is go over the basics of control systems. So with the basics of control systems, what you're going to want to know is there's multiple types of control systems. You have you have your proportional controllers. You have a derivative. I don't know what color starts with the letter D, so we're just gonna do like a deep blue. You have derivative. Oh Lord. This is mostly used with like a proportional derivative, so a PD or a PID. I'm also gonna cut this light. It's dark. Golly, bro. All right, cut that light. There we go. Now I got a nice, cool looking background. Um, my camera's at the top of the screen always. That's crazy. I didn't know that would happen. Had no clue that would happen at all. That's actually really cool. Um, and then we'll do this purple as indigo for integral. This can be a PI or a PID. So a proportional controller, um, the basics of that one, let me just go ahead and golly, that's a terribly drawn R. But you know what? It's fine. It's fine. Okay, so basics of a proportional controller, you have some type of reference point. So that would be like an R value that goes into some type of thing. So it could be plus, minus. This goes into this has an error or E, which goes into the control, I believe. The controller puts out some type of U or like a puts out a U or a like a signal or like an output. I mean an input, not output, input. Actually, I think this is the system. I'm gonna go back and check in just a second, but I want to make sure like I know what I'm doing before. I want to see if I know what I'm doing before looking at the stuff. So let's see. The controller puts out an output Y, and then if it's a closed loop, it'll have some type of feedback. But let me go back and double check and see if this is the right way to do this. Dang it, I should have trusted my instincts. I should have trusted my hot cheese and instincts, man. I got these two mixed up. And then um, if there's a feedback loop, there's a large amount of times where there will be a sensor to detect how much the outputs change. So yeah, there's also so like this would classify as a closed loop system. So like these are all closed loop systems. So these are closed loop systems. You can't have an open loop system, which is just like this. So you'll have your input, you have the error that goes into the controller, that goes into the system, and that leads to the output. So that's how open loop works. But in this class, most of what we're dealing with in terms of like the math and equations and whatnot are closed loop systems. So that is something to take note of. Okay, so that's the first basics of of control systems. So just as a just as a note for y'all, let me do this in this blue. Open loop systems are typically lower cost. They're more simple to build and calculate, but there's no feedback. Um, and that means like they're not very accurate and not very reliable. So I'll put those cons in red. On the other side of things, we have the closed loop systems. These are more accurate, more reliable. Um, and there is a feedback loop. However, closed loop systems tend to be more expensive and more complex and harder to calculate. Okay, so um the example that we were given in class that I will try to replicate here, so please excuse me if I do it incorrectly, was a motor and rod. Um, so essentially, instead of a motor and rod, well, actually, no, I'm just going to keep it motor and rod because that's easier to draw. So we have a motor, and this motor has a rod in the middle of it that we want. So this is where it starts. We want it to be, sorry, y'all, feel like I got a burp. We want the motor and rod to look like this. I am terrible at drawing. So we want it to be pointing at a 90-degree angle. But how do we get there? So there's actually an equation that we're given that we can use to calculate that. Um, to find the target force that we need. So we need a certain amount of torque. Honestly, just gonna copy this probably. Because I don't remember these equations and I don't want to keep going back and forth 1,000 times. So we have this equation, and these are the notes I took about it. So you have J times theta squared d2 d theta. Actually, that's yeah, d2 d theta plus the dampening force or the damping force multiplied by the velocity um added to the resistance, that's gravity and friction. um and then k theta is the, what is it, back imp. Oh, okay, there we go. I forget what that's supposed to represent, but that last variable means something. Um, and then you might be asking, like, well, what? How do you mean this is velocity, and how do you mean that this is inertia? Um, I can do the quick derivation over here real quick. So you have this. Hey, if you're in physics 206, don't panic mechanics. Might want to pay attention to this one right here. So let's say you have let's say you have a position R. You have position R, and that's a vector. Well, R being a vector really means that it's R times theta effectively. So if you take the derivative of position, so this is position, you take d dt with respect to time, you get dr dt. Um, no, no, hold up. You get r d theta over dt, and then this is your velocity, and then you take the derivative again, you get I think it's r d theta dt plus 2 dr d theta plus d2 r over d t squared. Shoot, I forgot how to take that. I forgot how to take that derivative. It's been a hot minute. I had to memorize it, and I've forgotten how to do it. It was something. It basically comes out to acceleration is the derivative of velocity. So, hey, go watch that video grades. That music video. I did it in that music video. Anyway, that's not the point. Um, so you're trying to get over inertia, the dampening force, the resistance of gravity, and then your K theta is, I believe, how much energy you're putting into the system. So if you want a proportional controller, we'll do this in the shade of purple, light purple. You're gonna have your starting reference point. There's gonna be some error coming out of there. So that's E. You're gonna want your controller to be your proportion. So KP, the gain of the proportion, times the error. Wait, hold up. No, not that's not it. No, it's not the proportion times the error. Hold up. Oh no, it is. It is. Um, then that has an input to the control system U. That fake freaking laugh, bro. Don't clip me. Please don't clip me. Then you have D2 theta, DT. Hold up. Yeah, so basically we just have that equation repeated. So I'm just gonna move up here so I can see it and then copy it and then bring it back down. And that equals the torque of the motor. You'll get the rotational angle theta out from that. And then you'll have that going into I think there's a feedback, but I can't remember what the feedback's supposed to be. Nope, there's just feeds back into its own thing. So that just goes into its own feedback, and that's where you get that's your proportional controller. Now we know the thing we want is 90 degrees, so we want um so our target reference. We'll say that this is 90 degrees. And what graph are we drawing? So this is the output graph. So we know it's going to start at 0, and as time goes on, it's going to increase. Geez, bro. Like this, the one downside about not drawing on paper is like you can't get the slide like paper. But it's going to increase, and it's going to come up just shy because there's nothing telling it to like there's like it's gonna hit and then drop and hit and drop and hit and drop, hit and drop, hit and drop over an infinite period of time. So our error will be in green, like emerald error. So our error graph over time, we know it's going to start at 90 degrees. So the error is going to be completely off, 100% off at the very beginning of what we're working with. So it's going to start right here at 90. And then as time goes on, that error is going to get closer and closer and closer to 0, but never quite actually at 0. And that's because we don't have anything like we don't have anything to offset the error at all. So there's no offset, which means there will always be an error. If we set KP um so the way you can calculate error, so calculating error, this is actually kind of important. Error is given as the output. Wait, no, it's the reference minus the output. To make it a little cleaner, for this one, it'll be R minus theta. So when the reference is 90, as an example, and theta equals 10, you would have your error equal to 80 degrees. So that's how that works. Reference minus the output. That's how that works. I don't know why I'm looking over here. Camera's right here. Look, my rib, my rib, my rib. Oh, my rib. That hurts. This live stream would be brought to you by Gatorade if they would sponsor me. but it's not brought to you by Gatorade. Oh, I forgot to change my thing to like Chris the Ninja. It's fine. Hold on, let me see if I can. I like for haven't done this in so long. I forgot to rename it. There we go. Wait, did it? There we go. Yeah, there we go. Now it's updated. Cool. Now it's really about to get complicated because now it's ninja time. It's ninja mode. So um if we set the proportion of the input gain equal to one, so if we say KP equals one, so we'll do pink for this. Hey, how's it going? Welcome to the stream. Thanks for being here. I'm just studying, it is what it is. But anyway, so you have a proportional controller, or proportions. Um, as time goes on, the proportion of how much it is, like the proportion depends on the error. So the error graph and the proportion graph, if KP equals one, should be exactly the same. So it should look something like this. And you should also be able to draw like a straight line through this. So I'm gonna do this in anti A&M fashion, good old anti A&M fashion. We're gonna put this in orange. You should be able to draw a straight line straight through it, and it should tell you um exactly the same thing. So that's what the graph should look like. That's not actually how it's going to work though. Unfortunately, because things never work as we expect them to work in real life. Can I get rid of this? Your boy out here with the knowledge. You know what I'm saying? Anyway, um, so let's say that KP equals 10. So if KP equals 10, well, not even that KP equals 10. Let's say that our graph, hey, let's say that the KP value or the reference value looks really weird. So this is so we have like a say KP equals 100. Well, we're going to start out um we're going to start out with our reference at 0. So this is our reference. We'll say this is 90 degrees. Well, this thing is going to shoot. It's going to go way up here and it's going to overshoot the reference point. So that means that it's going to either throw it into reverse or let gravity do its thing. So then the reference is going to drop down drastically. But then it's going to cross over at this point right here. And it's going to think, hey, we got to run this thing back. We got to run it back up. So then it's going to come back up. The input's going to change again. And it's going to cross at another point. And then it's going to say, hey, we got to go back again. It's going to come back down. And it might cross over one more time, or two more times, or three more times. But eventually it's going to come down and it's going to mellow out right along that line. Well, that's a lot of crossing the line, if you ask me. That's some drastic line crossing right there. But how does that affect our error graph? How does that affect our proportional graph? Well, it affects it quite a bit if we're being completely honest. So we're just going to go back to our emerald green. I can't speak English. I'm an engineer. We don't speak English. We speak numbers. All right. So our error graph. So the error will start out at 90. Draw a little bit down here. And then what color did I do the thing up here? I did a purple. Okay, yeah. I never represent. I got to sneeze. Let's say we're starting out here at 90. By the way, welcome to the stream. Thanks for being here. Appreciate you tuning in. Welcome. It's going to start here at 90, but it's going to drop way lower. Oh, I almost forgot to mark this one. So it's going to drop way lower and it's going to cross at that point there. Well, if you notice here, that's crossing at basically the same exact point that that the other graph is crossing at. So if you notice, like it's crossing at the same point. So then this graph is gonna shoot back up, and it should line right up with that other point. But now it's gonna shoot back around and hit that other point, and then the next point, and then eventually mellow out. Whether or not it actually hits zero, we have no clue. But you should be able to see a straight line, straight-ish line, because I'm not the greatest at lining everything up all the time. I was off a little bit. But essentially, you should be crossing over at those exact points. So I made a small mistake in drawing them, but like you see the first two lines cross over exactly. So really this should be crossing here. Then this one should be crossing. So yeah, that's where it should be crossing, and that's how the error graph looks. Now the proportional graph is going to look very similar. So we're gonna get our pink marker out again. Now I'm sure all y'all that are taking the class with me are like, Chris, why are you going over this basic stupid stuff, man? Well, look, man, somebody might be looking at this next year. They might need help with this. Dang, my bad. My bad. I ain't a genius. So if KP is equal to the error rate, then you'll have the same thing happen with proportional graph. Going to drop drastically, cross over, come back, cross over, come back, cross over, come back, cross over, and then so in this situation you may have a steady state error, and that's important to note. That's important to take note of. In systems, uh, excuse me, excuse me, thank you for loading OneNote in these situations where there is only a proportional, and I will write that in pink so that way y'all can really see it. And I'll even make it bold. There may be a steady state error. Gonna wait for the thing to catch up. There we go. And then things get a little bit more complicated. Let me check what the review was about. So let's skip ahead over the derivative and go straight to the PID controller. Because that's what's going to be on the exam. So a PID controller, let's see, what color should I use? So we have a we'll have a reference point. There we go. We'll have a reference point at R that will go into our PID. We'll have our proportional in pink. We'll have our ice blue for integral. And then we'll have our we'll have our derivative in like diamond teal. And all these get added up. I'm gonna try and bust out the maroon for A&M. Let's bust it out. That junk is hard to see. We're gonna bump the size. That all goes into the input that will then go to our motor control. Which then will have feedback into our reference. Dang, I've been studying for an hour. Yeah, productivity. Um, but yeah. Okay, so how's how are these graphs gonna look, man? How are they gonna look? So at the reference point, so our reference or output graph. Oh no, that's the theta. So output. Actually, I could probably do that on my own. You're gonna start at zero. You're gonna welcome to the stream. Thanks for being here. You're gonna want it to get to 90 degrees, but it's gonna go over a little bit and then probably come back a little bit. And then as it goes over and under, it will eventually balance out because it'll um the input will the the input signal will be controlled by three different criteria: the proportion of how much the error is off, which is this value here, the integral of how much the error is off. Excuse me. The integral by how much the error is off, and then the derivative of how much the error is off. Um, so first things first, let's get the proportional graph. Well, actually, no, let's get the error graph. As always, our error is going to be an emerald green. And then we'll draw the things in blue. So we have 1 point crossing here, 1 point crossing here, 1 point crossing here, one here, and then kind of one here. So we want these crossing points to line up with all the graphs. I'm going to draw them all the way down. So we know the error is going to start out. This is 90 degrees. Now the error is going to start out here. Then it's going to shoot way down. But nope. Error is going to start out here. Going to shoot down, cross, cross, come back, cross, come back, cross, come back, and then probably balance out right about there. And so we're actually crossing at where it's the points where we're crossing is where it's changing the place where it's getting different. So the integral graph is actually really interesting as it will never cross zero. So integral, what did I say? It was I said it was that blue, like the ice blue. So basically wherever the derivative or the error crosses the x-axis, that's when it changes from increasing to decreasing. So the integral graph would go like this to like this to like this to like this to like this. So it looks like a little one of those things right there. Whenever I say the word this nowadays, I think about that Game Grumps episode of Sonic Heroes. Where it's like, take this, take this, take this, take this. I don't know, like three of y'all are gonna get that reference, but I don't care. It's funny to me. So it's important to note that the integral graph will never cross over zero. And then wherever the integral graph changes direction, the derivative graph will also change direction. But in contrast to the integral, the derivative will actually start going negative first. So we'll start out going down, come back, go down again, come back, go down, and come back. And that should line up right along right where these peaks are. So that's PID controllers, how their graphs look. So the next thing that you should know is that these controllers need transfer functions to make them easier to solve. Because like you can't have signals where you have system controls in the same equation. For example, um, if you have, let's say that this is U, well, U is a signal, so this is a signal, and these are all blocks. So in order to get to the motor control, which we might call C, C equals U times, actually, let me do this for the corresponding colors. C equals U times KP times KI times K derivative. So how exactly are we supposed to, like, we can't have these two things mixing because these are all oh wait, plus. These are all plus. This U is multiplied. So we need to have a transfer function in order to get that like broken down into a more simplistic way. And let me try to find that. Give me just a second to try and find like the breakdown of where that thing is. There's a way to find the transfer function like really, really easily. Give me just a second, y'all. Hot cheese and crackers, bro. It's already 10 o'clock. It's 10 o'clock. Ninja, what? It's 10 o'clock. Golly. It sounds like these, I realize my voice is a lot deeper than I hear it. Like I thought my voice was like, it's 10 o'clock. But it's actually like, it's 10 o'clock. Like, but hold on, I'm trying to find the function. It's like 1 plus PC squared, something like that. Let's see. I swear I wrote this down. I swear I wrote it down. I know I wrote it down. Hold on, y'all. Like I'm trying to find it. Maybe it's after the implause inverse Laplace transform stuff. I know it's somewhere in here. Maybe the final value theorem. Okay, okay. I got you. I got you. The closed loop time constant. There's one thing that you'll probably want to take note of. You have PC over 1 plus P times C. And that's y of S over R of S. That will save you so much time. Write that down. Put that on your cheat sheet, bro. Put that on the cheat sheet. You need that you need that right there. If you can break it down to P, C, and if you can break it down to P and C, you're good, bro. You're golden right there. That's one of those things you really want to know for sure, for sure. So I want to go over the properties of the Laplace transforms. Let me see. I got to go back to the top for this. I'm so freaking sick of this. I'm so sick of this. Like I'm because my phone keeps falling, and so does my like my power strip. And my power strip unplugging my PlayStation. I'm gonna break something, and it's not gonna be something that the university paid for. I'm gonna have to pay for it out of my own pocket. Okay, this should not fall again. If it falls again, I quit. I'm ending the stream. If it falls again, I'm ending the stream. Uh, forgot what the linearity one was. What's the linearity one? Let me see. Okay, that's not really that important. Um, can I get a second to OneNote running real quick? All right, bet. No. Okay, here we go. Here we go. This is like confusing because I have to like scroll the opposite way that I'm thinking I need to scroll. Let's see. Which page is this? This is untitled. Oh, untitled page. Okay. All right, y'all. Apologies. Apologies. I'm getting there. Okay, so for a given function, you'll have a so let me scroll down. Scroll down. I could go through the derivations of this, but I don't really feel like deriving it for y'all. You're just gonna have to trust me on this. So for impulse function, so I'm gonna put the function on the left and the derivation on the thing on the right. And the way to write Laplace is you just do like that, and that equals some like F. Hold up, y'all.
Right, I just wanted to ask real quick, you know the like showers?
Yeah.
Is it like against the rules to like replace it with like a potential thing, like unscrew it?
Um, yes and no. So if like you damage the thing, like you damage the shower head, then you have to do the process of replacing it. And also everything that's in the room as it is now needs to be there when you leave. But if you replace it before you like, if you replace it now and then you fix it later, then you wouldn't know when you it's at your own fix.
Oh, okay, wait, cause like there's the people that come to clean, so I don't know if they're gonna like,
They shouldn't say anything, but like officially, it's supposed to be the way it is right now.
oh, you,
So if you change it, it's at your own risk. If it breaks, it's on you.
okay,
Because it's one of those things that they work on through the work.
okay. So it should be fine to replace it as long as you put it back there, right?
Yeah, as long as it's not broken and you put it back the way it was.
Okay.
I wish that was a more help. I wish there was like a more helpful answer, but like that's all I got.
Oh, yeah, no, you're good, it's, wait, and that's not gonna like affect cleaning or anything, right? Like, it's
It shouldn't affect me. Um, as long as they're able to still like use the shower water to clean the shower back out.
okay. Okay, yeah, thank you.
Yeah, no problem. Sorry about that, y'all. I'll probably cut that out. Well, I don't know. I don't know if I have to cut that out. I don't think I have to cut that out. Maybe I do. Maybe I don't. I don't know. We'll mute it eventually. We'll probably mute it on like the replay or something. I don't know. But anyway, back to back to my favorite thing. Oh boy, Laplace transforms. So the function, if an impulse function, that's like a function where you're going through time and then boop, and then that's it. The Laplace transform of that is just one. If you have a step function, which looks like this, then your Laplace transform of that is 1 over S. If you have a like a ramp function, that looks like this. That transform is 1 over S squared. If you have a function, like a natural function, which is like e to the minus at, which probably looks something like this. Excuse me. I think that's what it looks like. You'll have your your Laplace transform will be 1 over s plus a. If you have the natural function times a ramp function, so natural times ramp, which would be a t times I don't really know how that would look, but if you're given something like that, you would have 1 over s plus a, and s plus a is squared. With a sine function, um, that Laplace transform is omega over s squared plus omega squared. The cosine function, that Laplace transform is actually s over s squared plus omega squared. If you have a natural function multiplied by if you have a natural time if you have a natural function times the sine function, you have I think it's e to the at. I think it's e to the at. But I'll put a minus there. Times sine omega t. Then you get a Laplace transform of omega over s plus a squared plus omega squared. And then the natural function times the cosine function, which would be e times cosine omega t. That Laplace transform comes out to s plus a over s plus a squared plus omega squared. Now there are a few properties. So a couple the properties that you want to make note of. One big one is that there's linearity. 2 is the derivative property. Which states that S times F of S is the same as the Laplace of DFT over dt. Excuse me. Then you have the integral property, which is 1 over S times F of S equals the Laplace of the integral F of t dt. There is a time delay property. That's if you have e to the minus s times lambda. That equals the Laplace of f times t minus lambda. Now this pops up most times in sine functions. So that's where you'll see that pop up a lot most often. And then you have the last property, which doesn't they didn't give me a name, but you have f times s plus a is equal to the Laplace of f of t times e to the minus at. That equals e to the minus s lambda times f of s. So let's do an let's do an example. Sorry, I have to like blow my nose real quick. Um, yeah. So we have let's do g of x equals 8 cosine six t plus 6. So the first thing we need to do is we need to recognize that this is a time delay function right here. So this right here falls under time delay. So if we break down if we break this down to where 6t plus 6 equals 0, you can or so lambda is this value here times some constant. We set this equal to 0, we get 6t equals negative 6 divided by 6 divided by 6, t equals 1. So if t equals 1, that means that the constant times c is also equal to 1. So that way we know that we're dealing with truly 8 cosine times 6 times t minus lambda, where lambda is 1. So with the t minus the lambda, that gives us e to the minus s lambda. So that's e to the minus, oops, that's e to the minus s, because lambda is 1, times um 4 cosine or 8 cosine 6t. So that's 8 cosine of 6t. Well, that by the way, that's negative 1, but the negative cancels, so you just actually have to the s. Um, and that'll give you 8, because the 8 just comes down because it's not, you can't take the Laplace of a constant. You'll have 8 s over um s plus 6. Oh, I know, s squared, s squared plus 36. And that 36 comes from um the 36 comes from the 6t. Everybody's hopefully being able to keep up with this. I hope y'all are able to keep up, because this is 8 times s over s squared plus omega squared, where omega equals 6. So to simplify that together, we will now have 8 times e to the s times s over s squared plus 36. What's good, Beeman? Don't know how long you've been here while I've been rambling on, but welcome to the stream. Thanks for being here. Let's see what else. The last thing. I'll come back tomorrow and go over inverse Laplace, final value theorem, and how to do the cover up method and stuff like that. But I've been studying for an hour and a half, so like not too bad. It's also getting close to time for me to like go to bed. But I hope this was helpful. It helped me for sure because like I actually got my studying in tonight. But with that being said, I want to say thank you guys so much for watching this video stream. If you liked it, strike that like button like a ninja really would. Subscribe today to join the Shinobi. And I will see all you guys in the next study stream or the next live stream. I don't know. Maybe it's video. I don't know. I don't really care. Next time. Have a good night.